Now we move into a very important topic known as quantization. Quantization of the signal. This is what takes us from, remember we said that from a continuous time signal via sampling we produce a discrete time signal. Okay, this is discrete in time, it is continuous in amplitude, infinite precision for the representation. Now, if we go one more step where we do the quantization, then we will get x hat of n where it is discrete in time and discrete in amplitude, only a few finite number of discrete in time and discrete in amplitude. Okay. And the difference between infinite precision, continuous amplitude, this is infinite number of bits in the representation. This will have a finite number of bits in the representation. That is what we mean. Discrete in time we already saw as are the aspects. Okay. So now in the process of quantization, remember we said when you pass it through a sampling process, you must if you have not satisfied Nyquist criterion, then you will run into aliasing. So in order for aliasing never to occur, okay, there is a simple step that is done in A to D conversion. That step is called anti-aliasing filtering. Now, what is the response of the anti-aliasing filtering? So, HAA of j omega will be a filter which will remove all frequencies outside of minus omega s by 2 to omega s by 2. Okay. So, basically, because remember what we are doing is we are going to sample it at Ts, which is going to give me a sampling frequency equal to 2 pi over Ts. Okay. So, what this anti-aliasing filter does is that it will ensure that what you have at the output is a band limited filter, and it is band limited to half the sampling frequency, whatever the sampling frequency the C to D converter is going to do. Okay. So, this is guaranteed to have no aliasing at this point when I do the sampling here. Okay. No aliasing is the condition, and that is why we use something called an anti-aliasing filter. So, in the textbook you will notice that there is a subtle change in notation. The continuous time signal is xc of t. Now, it may or may not be band limited. So, before you apply it to a C to D, remember it is passed through an anti-aliasing filter, and this is a band limited signal. XA of t is a band limited signal. It has been filtered by an anti-aliasing filter. Okay. So, which means that when you convert it, it will be there will not be any aliasing at the other end. So, now when you talk about quantization and you see that the input is given as XA of t, you may say, well, you know what, maybe professor made a mistake in the previous slide. He wrote it as XC of t. This time he wrote as XA of t. No, it's not that we have changed the notation or wrote a different notation. It is just that XA of t is now has been pre-filtered, so that when you pass through the C to D converter, it will not have any aliasing. Okay, so this X of n does not have no aliasing. Okay, that is a important element, because the quantizer is going to introduce some distortion. We do not want aliasing also to come in, because that will add a complex distortion. So, all we want is the ability to take this discrete time signal, which has got a infinite precision in terms of its representation of amplitude. We are going to quantize it to a certain number of levels, and then say that this is going to be the expression for the quantized signal. Okay. I hope you are comfortable with that, because now we are going to look at what is the process of quantizing the signal. So, x hat of n has got a finite number of bits in its representation. Finite number of bits in its representation. Okay, we will say that this number of bits is b plus 1 bits representation. Okay, now why do you call it b plus 1? Why not call it some other number? This is the sign bit. Is it a positive or a negative number? And this is for the fractional part. Okay, so basically there is a sign and then there is a fraction which we will try to represent, and we will use the 2's complement as the representation for just to study. You can use any other representation also, but we will use the 2's complement representation for our study of quantization. Okay, so basics are all cleared. We are going to, there is no aliasing because of the anti-aliasing filter. We are sampling at Ts and we produce a discrete time sequence which has got infinite precision. We are going to convert it to a b plus 1 bit representation. So basically this is going to be the b plus 1 bits are the represented in this so basically this is the representation. Okay. Now let us quickly take a look at how the quantizer is supposed to work. Now if you assume that the discrete time sequence has got the input is on the x-axis. Okay, this is the input and the output is the quantized value. Okay, so the x-axis has the input discrete time signal x of n. Okay, so this is x of n, discrete time signal. It goes from some peak value to some value. So let us say that this one has got a maximum value in the range minus xm to xm. Xm is the maximum value. Okay, so the total range from positive to negative will be equal to 2xm. Okay, that is the range of values. So you can think of the maximum value here as minus some xm and the on the positive side. So again, just visualize that. We won't write it here. Okay, so if you remember, see here it is going from minus xm to xm. Okay, so the total input range is from minus xm to xm. Now, what is the quantizer doing? The quantizer says that if you are between minus delta by 2 to delta by 2, we will define what delta is. Okay, we will define this. If we are between minus delta by 2 to delta by 2, we are going to say that your value is 0 because of the quantization. Okay. Now, the minute you cross delta by 2, it is going to be delta, output is going to be delta all the way until you reach 3 delta by 2. So, this is a quantizer which is doing a uniform quantization, via rounding. Okay, what does rounding do? It says you take a real number, let us say you are a rounding of real numbers, 2.1 will be made 2, 2.3 will be made 2, 2.7 will be made 3. That is exactly what is happening here. Until you reach delta by 2, the value is 0. The minute you cross delta by 2, the output goes off to delta. Then it stays at delta until you reach 3 delta by 2. And then when you cross 3 delta by 2, it becomes 2 delta, then 3 delta and so on. Okay. On the negative side also, it is exactly the same thing. So, though the input can be continuous, can take any value from minus xm to xm, notice that the output will have only a finite number of values. Okay. Now, in this context, if you say that I am going to do a representation, b plus 1 equal to 3, that means 1 is for the sign, the first bit is for the sign and the remaining 2 bits are for the amplitude. Okay. So, the initial level is considered is called 0, 0, 0, then 0, 1, 1, 0, 1, 1. So, basically those are 3 levels, and on the negative side you will get 1 and then because it's 2's complement, you will get 1 1 1 0 0 1 0 0. So basically this is the 2's complement code, and if you want to write it in terms of fractions, which is sometimes helpful for us to visualize, think of this as 0, think of this as 1/4, 1/2 and 3/4, and this as -1/4, -1/2, -3/4 and -1. With 3 bits, you can get 8 levels, and because you have chosen one of the levels to be at 0, remember that though it looks symmetric, you will have one extra level either for the positive or for the negative. By convention, we have taken it that extra level on the negative side. Okay, so basically this is the representation. Now, any value that you have between in this range, when you pass it through a quantizer, it will give you exactly 3 bits. If it is a positive number, the first bit will always be 0, and these next 2 bits will decide whether it is between 0 and 0.25 or between 0.25 and 0.5 or between 0.5 and 0.75. So this is going to be the representation that we have. So if you write down the B bit representation as A0, A1, A2, okay, these are the 3 bits. Okay, 2's complement says I am going to use A0 for the fraction. This is for the this is for the sign. This is for the sign, and this is the fractional part. And let me remind you that the 2's complement, you will obtain the value of this number in the following manner: minus A0 times 2 power 0 plus A1 times 2 power minus 1 plus A2 times 2 power minus 2, and if you have more bits, it will go on further from here. Okay, so basically this is how we will get the representation of the signal. Now, what is the I have used delta by 2 as a step size. So can we sort of quantify that? So if x of n, I am just giving you a couple of examples, is greater than or equal to minus delta by 2 or less than delta by 2, then the output is going to be 0, 0, 0, 0. Okay. And if my x of n, so basically this will be output will be 0, 0, 0, greater than or equal to delta by 2 and less than 3 delta by 2, then I am going to get 0, 0, 1. Okay, so now you can see how this is basically the quantization aspect that is happening. Now, what we would like to do is study the effect of the quantizer and be able to understand and apply it in a very systematic manner. So, I hope you are able to visualize how the input from minus xm to xm can be broken into segments, which will then be represented by means of a finite number of levels on the positive side and a finite number of levels on the negative side. All right. So let us take the next step in terms of the so this step size that we are using, step size delta. Remember, it is going from minus xm to xm, so the total range is 2xm, and how many levels are there? The number of levels is 2 to the power b plus 1. If there are 3 bits, then if b is equal to 2, then you have 3 bits in your representation, so 8 levels. So basically the size of delta is the total range divided by 2 raised to the total number of bits. So this is the same as xm divided by 2 power b. This I am going to cancel off this 2 and one of the 2. So basically this is the representation that we have. Okay. So now what we are going to be looking at is the quantization operation itself. I have x of n passing through a quantizer and coming out as a quantized value. Okay. Now, we can visualize, obviously x of n and x hat of n are not the same because of the quantization. We are going to say that this is equivalent to the input x of n and an error term, which is the effect of the quantizer, okay, to make it either go to the lower level or to the higher level. So, E of n can be positive or negative, right, because depending upon how the quantization is happening. And this is going to be x hat of n, which is given not as a quantizer, but as the input signal plus a random error signal. Okay. Now, what is the range of values of E of n? Go back and look at it. What is the maximum error that can happen just before you get to delta by 2? What is the value? It is 0. Just afterwards, it becomes delta. Okay. So, if you had a value that was very close to delta by 2, then remember that you are either going to give it as 0 or you are going to give it as delta, in which case the maximum error is in the order of delta by 2. Similarly, on the negative side also, the maximum value, maximum is delta by 2, minimum is delta by 2. Now, we say that this error is a random signal, because it depends really on the value and how we are going to quantize it. This error goes from minus delta by 2 to delta by 2, and in terms of its probability, the error is uniform in this range. It can take on any of these values with equal probability. So, you think of this as a uniform random variable which goes from minus delta by 2 to delta by 2. Okay, so this is the probability of the error signal. Okay, probability of the probability distribution function of the error signal. It is a uniform distribution. Uniform distribution, the probability is the same for all of them. Remember that the area under the PDF should always integrate to the value of 1. So, this one has to be equal to 1 over delta. So, this is the so what are the characteristics of the error signal? Okay, this is an important set of assumptions. I would like you to be very careful, and if you have any doubts, we can discuss it more, or you can also do some additional reading. Characteristics of the error signal E of n. Okay, here are some assumptions. Some of these terms may be not so familiar, but we can always explain. But basically, this is taken from random process theory. So, E of n is said to be a sample sequence of a wide sense stationary random process. Sample sequence of a wide sense stationary random process. WSS random process. Okay. Now, we will again, you may know what the properties of a wide sense stationary random process are, but even if you are not familiar, basically think of it as a random process which has got certain properties. Okay. Now, the second property that we are going to be highlighting for E of n is that the error sequence E of n, error sequence is uncorrelated with the input sequence, uncorrelated with x of n. Okay. Now, x of n may have a positive error, negative error, small error, large error, completely error and x of n do not have any correlation. Whatever is the value of it, the quantizer is going to decide what the error of n is. So, that is what we say is that x of n is doesn't have any correlation with the error sequence. Okay. Now, this third property is very important. The error that occurred on x of n and the error that occurred on x of n plus 1, the next sample, there is no relationship between these two. For example, x of n could have a negative error, x of n plus 1 could have a positive error. Again, these are completely so this is what is the most important. E of n is a white noise process, white noise random process. Okay, so white noise means E of n is not correlated with E of n plus 1. Okay, so you can treat E of n as completely independent of E of n plus 1. Okay, knowing E of n does not tell you anything about E of n plus 1 or E of n minus 1. So that is what is, and of course the last property we already sort of justified it. We said that the probability distribution function PDF of the error signal, which is PE of E, is a uniform random process, is uniform. CDF is uniform. Okay, so basically it is a random variable, error is a random variable, it is not correlated to the signal, it is not correlated to other values of E of n, and it has a uniform distribution. Okay, so the first step is to compute the mean value mu e. How do we do that? This is minus delta by 2 to delta by 2, that is the range of that, E times PE of E times DE. Okay, PE of E is 1 over delta. So, 1 over delta integral minus delta by 2 to delta by 2 E times DE. So, this is 1 over delta E squared by 2 from minus delta by 2 to delta by 2, this is equal to 0. Okay. So, basically we say that this random process, E of n is a random process, and E of n the mean value is 0 because it can be positive or negative, and with uniform probability from minus delta by 2 to delta by 2. Okay, that is a first result that I would like you to make note of. The second result is the standard deviation or the variance of that. So, the second result is sigma E squared is given by, because it is 0 mean, we can straight away write down the expression minus delta by 2 to delta by 2 E squared PE of E DE. Okay, that is the probability distribution function. So, this will come out to be 1 over delta minus delta by 2 to delta by 2 E squared DE. So, that will be 1 by delta E cubed by 3 divided by minus delta by 2 to delta by 2. Okay. So, this you can verify comes out to be delta squared divided by 12. Okay. So, a very important result, and now if you go back and look, we said that delta was equal to, if you go back and look at that expression, it was xm divided by 2 power b, am I right? So, this can be written as 2 power minus b times xm. So, sigma E squared can be written as 2 power minus 2b, because you have to square delta squared, xm squared divided by 12. Okay, I hope you are comfortable with this expression. So, what have we said so far? The error signal, when you pass through a quantizer, looks like you have taken the original signal and you have added an error signal. And this error signal is a random signal because it can be positive or negative, small value, large values, anything between minus delta by 2 to delta by 2. Okay. Now, we wrote down the properties of E of n, that it looks like to be a sample sequence of a Whitson stationary random process. The E of n does not have any correlation with the input signal x of n, neither does it have correlation with E of n plus 1 or E of n minus 1. It is a white noise process and it has got a uniform distribution. Using the property of a uniform distribution, we have obtained the mean value and the variance. Now, why did we do this, this step? Because we want to now compute what is the signal to quantization noise ratio. Okay, signal to quantization noise ratio, quantization noise ratio, SQNR. Okay, sometimes they call it SNR, but SNR is has got a different interpretation in the context of communication. So, in signal processing, maybe to be precise, we can say that we are looking at the definition of signal to quantization noise ratio. Okay, so we define the signal to quantization noise ratio as 10 log 10 because we want to convert it into a dB scale. The variance of the signal, sigma x squared divided by sigma e squared, which is the quantization noise. Okay, what is the power of the signal and what is the power ratio of the power of the quantization noise? So, these two are very, very important quantities and this is what we are, and we know we have an expression for, so basically we have an expression for the variance of the quantization noise. So, let us substitute 1 in 2. So, substituting 1 in 2. Okay, 1 in the expression for 2, we get SQNR to be equal to 10 log base 10. Okay, we can sigma e squared is at the bottom, so it becomes 12 times 2 power 2b. Okay, because that's in the, and we have sigma x squared divided by xm square. Okay, please make sure that you are, when you substitute, we are getting this expression, that there is no, you have not made any mistake in our in the representation. Now, look at this ratio. Okay, what is sigma x squared? This is the energy of the input signal. Input signal. Okay. Now, what is xm? It is the range in which this input signal lies. Range, the maximum value, plus xm and minus xm. Range of the input signal. Okay. So, now comes a very, very important aspect, that if you allow the energy range of the input signal to be large, then what will happen is your signal will exceed the plus and minus values, and then what you will get is something known as clipping. Because remember, when you go back and look at this particular figure, let us see which one here. Okay. Now, if you go beyond xm, what will happen? You are going to get a constant value. So, this is known as clipping. Okay. Anything beyond this is called clipping. On the positive side there will be clipping, on the negative side there will be clipping. That is a type of distortion. We do not want that distortion to come into play. So, we want the signal to be as much as possible within the range of plus xm to minus xm. Okay. And to be on the safe side, we usually design the signals in the following manner. Typically, we design sigma x to be equal to xm divided by 4, a factor of safety. Basically, you want the standard deviation of the signal or the signal power to be well within xm squared. Okay. Now, if you now substitute this back into this expression, then you will get a very, very interesting result. So, let us first look at this particular, let us simplify this expression. What you get is 10 log base 10 2 power 2b, okay, plus 10 log base 10 of 12. Okay, that is a constant 12. minus 20, because the xm squared and sigma x they are squared. So, 20 log base 10 xm by sigma. I took the inverse ratio. So, instead of taking just plus log, it is minus log xm by sigma x. Okay. Now, substitute xm by 4 over here. Okay. Substitute 3 in 4. 3 in 4. So, this is SQNR. So, what we will get is a value which is SQNR equal to 6.02 B minus 1.25 dB. Okay, this is a very, very important result which tells you what is the quantization noise ratio, quantization noise impact on the signal. Okay. So, for example, if you say that your B is equal to 16 bits, okay, SQNR is equal to 96 minus 1.25, which is approximately 94.75 dB. Is 16 bits. That means you have reduced the quantization noise is very small. On the other hand, if you have quantized it to 4 bits, you can then see what will be the signal to quantization noise ratio. Your quantization noise is going to cause a lot of impairments into your signal. Okay. So, let me summarize what we have started with, and let us re-look at all these things. Okay. The first thing is, we said that before you do C to D conversion, the typical practice is to pass the signal through an anti-aliasing filter, which will be from minus omega s by 2 to omega s by 2. So, this will guarantee that when you do the conversion, there will not be any aliasing. And the signal that has passed through the anti-aliasing filter is denoted as x subscript a. Now, if x of a was already band limited and was in that case it did not need an anti-aliasing filter. So, the anti-aliasing filter does not do anything to further reduce. However, if the xc of t was wider than the omega s by 2, then the anti-aliasing filter will chop it off. So, for example, if xc of t was like this, then you can see what would happen. Okay, so this is xc of j omega. Okay, so red is xc of j omega, and what will be the spectrum of xa will be the purple one. Okay, so this is xa of j omega. Okay, so basically it cuts off that portion which lies outside the window, so that Nyquist rate will be satisfied. Now, once you have that, then what we are looking at is how does the quantizer work and what sort of distortion that it introduces. We said that we will use a b plus 1 bit quantizer, where the 1 bit is used for the sign and b bits are used for the fractional part. And one way to represent it is from plus 1 to minus 1 in the range that is given to us, and one of the mappings that we have shown. This is a uniform quantizer which is implemented via rounding operation. Okay, and we showed how we can do the sign representation and the fraction representation. We showed what is how the quantization works and what is the range of error for the quantizer. And we said that the quantization error looks like to be a random quantity which goes from minus delta by 2 to delta by 2. The maximum value is plus delta by 2, minimum value is minus delta by 2, and it is uniform in this range. And given that it is a uniform random variable, we then we computed the mean value and we computed the standard the variance of that. Now, we computed it and obtained a very important result which said that the variance of the quantization error depends on the number of bits that you have used. If you have used more bits, the variance will go down. If you have used less bits, the variance will go up. Okay, so again the number of bits plays an important role here, and from here we said that there is a very important parameter that we would like to look at in the context of quantization. It is signal to quantization noise ratio. Sigma x squared is the signal energy divided by the energy of the quantization noise. The ratio of these two energies, you take it as 10 log 10, you will get a value in dB. This is the signal to quantization noise ratio. Now we substitute the value for the variance of the standard quantization noise, and then we say that the variance of the input quantity is typically chosen to be less than a safety factor less than the peak value. So we take it to be xm over 4, and once you take that, then you get a relation. You can take xm by 2, there is a chance that you will run into clipping. So to be on the safe side, you want to make sure that your signal is well within the peak value. And if you take xm sigma x is equal to xm by 4, then you will find out that you will find the relationship between signal to quantization noise ratio and the number of bits is given by SQNR is equal to 6.02b minus 1.25 time this whole value in dB. This whole value in dB. Now, this is what is commonly given as a statement minus 6 dB per bit quantization. Okay, this is a thumb rule that is often quoted. They say that it is minus 6 dB per bit. Where does that come from? Comes from this formula, because if I increase from 6 bits to 7 bits, the signal to quantization noise ratio will improve by 6 dB. If I go from 7 bits to 8 bits, another 6 dB. So that is what is the represented. So this is a what is called a rule of thumb for quantization. For quantization. Okay. And I hope you are, you may have to use it. Sometimes they may say, okay, if you want to get 100 bits of, 100 dB signal to quantization noise ratio, how many bits should you use? 16 bits will give you 94.75. 17 bits will push you to 100 dB signal to quantization noise ratio. So 17 bits is the answer. If you were to use this simple formula where you with the assumptions that we have made, this is the answer that you will get, and it's usually a fairly accurate answer to give if you are if you have to estimate the number of bits needed for the representation of your signal.